Welcome to IA201. We're doing a book review for Chapter 7. And in Chapter 7, this particular book talks about solenoids in solenoids. And solenoids are sort of the meat and potatoes of the electronic control world in the first of all, they were the entire mechanism for all sorts of automatic control back 50 or more years ago. In today's world, they are a way of converting a very low voltage signal into a higher current or higher voltage signal, on-off signal. So they're a great way of using a small voltage and a small current to control a larger voltage and or a larger current. So you're going to find these embedded inside of PLCs. We have little bitty optically isolated relays with tiny solenoids that control voltages straight out of a PLC. So they're built into the motherboard of a PLC. And you're going to find them built into panels where we're controlling with a small PLC a much larger voltage that will screw up the PLC. And of course, you're going to see these in virtually every motor starter circuit. So these are critical for running motors, because motors, not only do they create a large, they usually large amount of current usually and voltage required to push them around, but the motors create a lot of EMF, electromagnetic frequency noise, and so it's very difficult to control them from an electronic device without screwing up that device. So in many applications, you have to have a relay or a contactor or a motor starter to run a motor from a PLC or any other electronic, electronic device. So motor starters, therefore solenoids, are critical. Chapter 7.1, electromagnetics, just gives you this should be a review from high school physics and perhaps also review from ELEC 153. It talks about how a magnetic field is created by a coil of wires. And pretty much everyone intuitively understands this. You take a coil of wires and you run a little bit of a current through it, and you can create a magnetic field. A lot of people did the experiment with, kind of a battery and a steel nail and a coil of wire, and then you can kind of create this little electromagnet if you run current through that coil of wire. And the book talks about the left-hand rule, which is the idea that if you take your left hand and you grasp a steel, like a steel component, in other words, and you hold it like this, has to be your left hand. If you run your coils this way, so the coils are running, in this direction from negative to positive, then the north pole of your magnet you create is going out in the direction of your thumb. So that's the concept behind the left-hand rule. It just says where the north pole will be in the magnet that you're creating. So I don't know if that's super obvious or very useful, but it's something that's interesting. So just understanding that electrical current can create a magnet is really the critical thing here. In 7-2, we talk about solenoids in general, and it talks about the various solenoid configurations out there. There's a lot of different kinds of solenoids because you can position a magnet that sucks in a contact in a lot of different configurations. For instance, right here, we have the contactor that I mentioned, and down at the base, you've got your coil. There's your little coil of copper wire. So that little coil, one end is attached to this tab, and the other end is attached to the tab on the opposite side. And so when I energize this coil, then what happens is this entire metal frame down here gets turned into a magnet, and it sucks down. Remember, we popped this open, we found the contacts inside there, and it sucks down the metal frame that's spring-loaded and mounted with contacts. So it basically sucks one magnetic plate down against another magnetic plate. So if I press this down, this whole thing is spring loaded, and it's attached to a piece of metal, a little steel plate that gets sucked down. And then, so this, all I'm doing here is creating a little magnet that sucks down this plate against the force of that spring. So the spring separates them, and then the magnetic force sucks it down. And that creates my solenoid. And that's one configuration, right? That's a vertical action. On this particular relay, we've got another coil right here. This coil right here, this little thing that's wrapped in yellow tape, is also a copper coil of wire. It's got two contacts that go down to these two leads on the base plate. If I give it DC power, the other one was AC, this one's DC, it actually creates the electromagnet, and there's a little steel core. You can see the end of the core sticking out of this. The front of the core is right there. You can see it just peeking out from the front of that coil. That sucks this plate. There's a magnetic plate right here. When that turns on, it creates a magnetic field and sucks this plate across against it. All right, you can see it doesn't have far to throw. That plate just goes right up against it. And that coil right there creates the contact closure between that contact and that contact. See, normally closed are these two contacts, normally open are these two, until it turns on, and then they close. All right, so that's a pretty typical kind of orientation. Is that? That's a clapper orientation, where you've got a plate that gets sucked up against a coil and then causes that contact to be made once you suck it up, kind of make that contact. So these are all different configurations. The actual configuration doesn't matter. Let me just divert a little from the book. What matters is the coil replaceable on the solenoid that's broken? Because one common failure point is, for any kind of relay or contactor, is the coil. The coil itself is constantly being heated up and cooled down. Anytime you energize it, it slightly warms up. Anytime you de-energize it, it slightly cools down. And so, and we're going to go into troubleshooting later on. Also, high voltage or low voltage can burn out a coil for different reasons. So replaceable coils, in the case this is an ABB contactor coil, is critical. And so recognizing the coil, how you can remove it, how to specify that coil, how many volts is it? Very, very important. What kind of voltage does it take? Need to match it exactly in terms of configuration, size, the little hole, the steel parts of your magnetic configuration need to match exactly. So buying this coil can sometimes be a very tricky process. So you've got to do that right. So let's talk about some configuration, or I'll call it solenoid construction components that are very important. Two key words you need to know about are eddy current and armature air gap. Very important. And there's on this page, it doesn't really it describes what's going on, but let's look at the really more interesting pages, which is the next page on 176. In figure 7.4, it gives you an idea of what those eddy currents are. What happens. AC solenoid's magnetic assembly and armature consists of a number of thin pieces of if you look in here, these what you see the edge of is many thin plates all screwed together, and those they kind of look like this. So there's two key aspects to how this works. Number one, you've got eddy currents that are created in that steel. Number two, you have to have an air gap that's critical to making it work properly. And if you have dirt or whatever causing a problem with the air gap, it'll slow it down or even make it not work anymore. Number three, you've got something special built into an AC circuit called a shading coil that if this gets cut, it will also keep it from working properly. The shading coil is a single turn of a usually copper, but any kind of conducting material mounted on the face of these laminated steel stacks that keeps it in holding against the armature for AC circuits. So in an AC circuits, the current basically drops to zero every 1/60th of a second. So by using a shading coil, it creates an extra time frame where you're maintaining your magnetic field, and keeps that coil against, enables your magnetic circuit to continue on even when every 1/60th second there's no current. That's a very important feature. If that breaks, you're going to get chatter. It's going to chatter at 1/60th, basically 60 cycles per second, which is what AC electricity is in the US. So that's an important concept. Once we get to page 177, section 7-3, we talk about basic solenoid characteristics, how they're built, how they're encapsulated. You have a covering on the coils in many cases. And, both the coils I show you, this covering is clear plastic. You can see it shiny in there. This coil right here has some sort of probably a nylon or PVC covering on it. And so you want to protect your coil for a long life, especially in industrial environments where you have a lot of grease or things that might be breaking down the copper. So you have to look at the specifics to the coil. In the case of this coil, this has a high temperature nylon wrapped around it to protect it. And that basically that's a higher dollar coil, and that will last longer in an industrial environment. It's designed for a contactor. Another key fact about coils and any kind of energizing of a coil, just like energizing a motor, you've got something called inrush. So when you first turn it on, you get a whole bunch of extra current. So anytime you fire up a coil, you get extra current. When you have it on already, the ceiling current is usually much lower. But the interesting thing to me is 6 to 10 times your current to turn it on than it is to keep it sealed. That little burst of energy, and this is where I'm going to divert from the book. If you have one of these big coils, right, and let's say you run a communication cable nearby to that coil, this is a USB cable, but it could be a communication cable or a cable associated with a sensor. If you run this coil right near this cable, guess what happens every time this contactor turns on? This particular cable will receive a big burst of EMF based on that inrush current. That big burst of EMF may screw up the data going into the device hooked to that cable. And you may get these weird problems that you can't track down because every once in a while, boom, you get this weird chunk of data, and it only occurs when this thing's being closed at the same time as you're trying to receive that data. So this is a classic example of weird problems that occur in automated systems that are associated with motors and also contactors. And sometimes even smaller relays like this, though that's pretty unusual, a little DC relay. Sometimes even smaller relays like this will cause a little bit of an inrush, and you'll get that weird bump of static on your sensors, and they'll cause a problem. Key aspects of a coil, I'm going to highlight 3 terms that are critical: pickup voltage, seal-in voltage, and dropout voltage. Pickup voltage is especially critical in low voltage relays that are associated with devices that might be built onto your PLC. Pickup voltage is just enough voltage to cause that relay to close. Seal-in voltage is just enough voltage to keep it closed. And dropout voltage is the point by which when you reach that lower voltage, it pops open. That's your dropout voltage. So those are very important terms. In general, for industrial controls where I've got relays like this or contactors like this, my voltage tends to run pretty consistent. You know, it's 110 volts or 220 volts or 24 volts DC throughout my system. But every once in a while, you'll run into an application where, because of the way this is wired or the plant you put this in, it's running right at the low end of its voltage range. And if it does that, then knowing that your contactor has a pickup voltage or dropout voltage at a certain point is very, very important, because then it helps you diagnose problems. Various problems you can have with the solenoids is excessive voltage, low voltage. Excessive voltage can cause a variety of problems. A lot of heat added when you put too much voltage in there, early failure. Low voltage actually creates high current, also could create failure. These are pretty classic problems with any kind of solenoid. We've got a variety of selection methods, very important, push, pull, mounting. There's a lot of different ways of setting up a solenoid. For your part, I didn't highlight any of these because you're probably not specifying a solenoid, you're specifying a device and that will have a solenoid in it. On page 179, we get into solenoid applications. This is all good data. I haven't highlighted anything in this section because it's just good background data. It talks about the use of solenoid in valves, talks about the use of solenoid in relays, and then it talks about all the places where you can put valves and relays. So it's generally interesting. And here they talk about a lot of details about valve actuator. And in your IMT 110 class, which is your pneumatics and hydraulics class, you will dive into these. You will need to know all of these different valve actuator symbols and how they work. Here, not so important, but you've got a place you can look things up if you need to, for homework, for instance. All right. It also mentions pneumatic robots, which are very, very limited. Right now, there's only a handful of places you find them. So really not critical from my standpoint for you guys in this course, but read about them. They're kind of cool. The idea that you can run an entire robot from air using solenoid valves is pretty cool. The section which I think is excellent, really, really important, is 7-5, starting on page 184. Troubleshooting solenoids. Guys, if there's one reason to keep this book and not rent it, it's these troubleshooting tables, right? So if you may want to just copy out these tables, even if you're renting your book, and keep them in a binder, because they're very useful to help you organize your troubleshooting steps anytime you've got a problem with the solenoid valve or a relay or a contactor. It just steps you through the possible failure modes and how to fix them. I've already touched on most of the content here, so I'm not going to go through it again, but the content itself, by just having in a single table kind of a step-by-step problem, possible causes, comments, and how you verify the causes. It's really, really good. It also mentions, I forgot to highlight this. I mean, incorrect voltages is your classic reason for failure in solenoid valves or relays. But transients means a high voltage or a low voltage that's very brief. A short-term higher low voltage, it's transient. And the high voltage is really the killer for these relays and solenoid valves. And so that's the important thing they mentioned here. Rapid cycling, that's clicking on and off really fast. We've talked about why that may occur. it sometimes occurs because your circuit is actually turning on and off that relay really fast, and something is wrong with how you've designed your circuit. Sometimes it occurs because something broke in that relay, such as the shading coil. So that's pretty much it for chapter 7. Here on page 186, it gives you a couple of classic ways to test a solenoid circuit. Pretty straightforward, nothing magical about that.